Al, I'm here with updates on my knitting machine project. If you didn't see my last video, I bought a Brother KH910 knitting machine, which is an electronic machine from 1980. And I'm in the process of reverse engineering it so that I can modernize the control systems. In my last video, I took apart the pattern subsystem to see how it works. It turns out that the main control board drives a motor, which moves an optical head back and forth across a pattern like this. The optical head then produces an analog signal that corresponds with the line of pattern that it just moved across. In this video, I'm going to replace that subsystem with an Arduino. I've broken the project down into 2 steps. Step number 1 is going to be figuring out how to generate an analog signal with the Arduino. I plan to use onboard hardware to output a series of voltages that will approximate the analog signal. Step number 2 is going to be taking the motor signals from the control board and using them to trigger the generation of the analog signal from step number 1. I'm going to do this by physically connecting the motor signals to interoperable GPIOs on the Arduino and triggering a pattern generation whenever an interrupt from the external source fires. Let's get started. First up, generating an analog signal. Microcontrollers, like these Arduinos, are digital systems, which means that they are best suited to deal with signals that have only 2 states, high or low. This is an example of a digital signal where high is represented by 5 volts and low is represented by 0 volts. However, analog signals, like the one I captured in the last video, are continuous and express more states than just on and off. You can see that this signal has 3 different voltage levels that it uses to express the pattern data. So how do we turn a digital signal into an analog signal? There are tons of ways to do this, but the ones that I am most familiar with, and more importantly the ones that I have parts for, are using pulse width modulation or using a digital to analog converter. Pulse width modulation, or PWM, consists of pulsing a digital pin at a high frequency with differing ratios of on and off time, or different duty cycles. For example, the first part of this signal has a 43% duty cycle, meaning it is on for 43% of the time, and the second part of the signal changes to an 88% duty cycle, meaning that it's on for 88% of the time. When this signal is passed through a filter to remove the high frequency components, you end up with about 1.6 volts and about 3 volts. The second method I mentioned is using a digital to analog converter, or a DAC, which is a piece of hardware that essentially does all of the work of generating and filtering a digital signal for you. Fortunately, one of my Arduinos has a DAC built in, so I am going to just use that to create my signal. This is the first version of the code that I've written. I'm not going to go into excruciating detail here, but this and the rest of the code from this video will be up on my GitHub. At a high level, this code works by shifting through the pattern of bits that I defined at the top of the file. For a 1, it will set the output voltage to a value that represents a dark square, and for a 0, it will set the output voltage to a value that represents a light square. I calculated the light and dark square values using a linear equation to map the minimum and maximum output voltages to the minimum and maximum values that the DAC takes in. The hardware setup for this code is fairly straightforward. The logic analyzer ground is connected to the board's ground, and the logic analyzer channel 0 is connected to DAC 0. Let's see what we get when we run the code. This is promising. We have a nice defined square wave. But unfortunately, it looks like the maximum voltage we're getting is 2.7 volts. I think that's going to be a little bit too shy of the 3.6 volts the original signal was. The DUE operates on 3.3 volt logic, meaning that the highest voltage it will be able to output is 3.3 volts. I was hoping the DAC would be able to hit that full 3.3 volt range, but it was only able to get a maximum of 2.7 volts, probably due to some loss in the hardware. Unfortunately, I feel like the maximum of 2.6 volts is just going to be a little bit too low, so I'm going to try again with this other board instead. This is the DUE Milnova. It operates on 5 volt logic, so it should have a better output range. Sadly, it doesn't actually have a DAC on board, so I will have to use the PWM method instead. Here's the modified code for the new board. I only needed to change the output pin and the maximum expected voltage level. I have the maximum voltage set to 4.84 volts instead of 5 volts because that is the real value that I measured. Other than that, the rest of the code is identical. You can see that we are definitely getting different duty cycles. Next, I'm going to need to build a filter to turn this signal into an analog waveform. I'll give a few more details about how to do this in a second, but first let's take a look at what that new waveform will be. This signal is a lot closer to what we need. You can see that the PWM has been smoothed into these sawtooth waves and that the voltages at each point are what we are looking for. However, the frequency of this signal is not correct yet. This signal is something like 5 Hz and I need it to be closer to 300 Hz. It's important that I get the frequency fixed before spending too much time fiddling with the RC filter circuit, because the filter characteristics will need to change when the signal frequency changes. To make the frequency adjustments, I calculated the correct delay times in microseconds instead of milliseconds to give us enough accuracy. And during this process, I also realized that I needed to increase the PWM frequency in order to keep up with the new signal frequency. We're still able to get a nice PWM signal, but the filter is definitely not happy. An RC filter is a combination of a resistor and a capacitor. The filter will let different frequencies through based on the frequency cutoff formula, 1/2 pi times RC. There are two different configurations that you can arrange the filter in, a low pass or a high pass. Low pass means that any frequency below the frequency cutoff will pass through the filter, and anything above the frequency cutoff will be filtered out. And high pass is exactly the opposite. Frequencies above the frequency cutoff will pass, and frequencies below will be filtered out. For this project, I will be using a low pass filter so I can filter out the high frequency PWM signal in favor of the generated pattern signal. Time to dust off that old circuits toolbox from college. I knew it would come in handy at some point. If I remember correctly, I should have a couple bags of random components in here. Let's see what I can find. Okay, I was able to find enough components to have a few different filter options. I've laid the filters out in a breadboard and I'm connecting up my Arduino as well as the Saley to the board so that we can get the signals. The first filter that we're going to look at is on the left. It is a 2.2 kilo ohm resistor with a 470 picofarad capacitor, so super small, and the cutoff frequency is 150 kilohertz, so a very, very high cutoff frequency. To create the low pass filter, I have the output pin connected to the resistor on the right, the Saley coming off of the joint between the resistor and the capacitor connected through to ground. So this signal looks almost identical to the signal we were getting off of the PWM pin. Very little filtering has actually happened. We definitely need a stronger filter than this. The next filter has a much lower cutoff frequency of 72 Hz. This signal has been smoothed out a little bit too much and doesn't give us the voltages that we actually need. And our last filter is 885 Hz with a resistor of 180 ohms and a capacitor of 1 microfarad. This signal looks much, much better. Not entirely perfect, there's still a bunch of bumps that haven't been entirely smoothed out, but I'm hoping this will be good enough. Okay, finished with part 1. Let's move on to configuring interrupts. So this is the original signal. For the emulator to work correctly, I need to generate the pattern in response to one of these motor signals instead of once every second. To do that, I will need to take each motor signal into the Arduino as an input. But first, I need to figure out how to take these 10-volt signals down to 5 volts. If you recall, the Arduino operates at 5 volts and might just let out the magic blue smoke if I try to input a 10-volt signal. I'm going to use what's called a voltage divider to bring the 10-volt signal down to 5 volts. The voltage divider works by dropping the input voltage over R1 to get a lower output voltage. The output voltage is going to be equal to the input times R2 over R1 plus R2. So for example, if the values of R1 and R2 were equal, you would end up with Vout equaling 1/2 of Vin, or Vin divided by 2. I selected a 680 ohm resistor and an 820 ohm resistor. This will give the Arduino 45% of the incoming voltage. I went slightly lower than 50% to hopefully compensate for any voltage spikes, It's not perfect protection, but it's better than nothing. The motor signal will go in here, the Arduino input is pulled from here, and finally, this resistor drains to ground. Now the code needs to be modified to take the motor signals as interrupts and generate pattern signals at the right time. These lines attach interrupt routines to the motor pins. This means that anytime the voltage changes from low to high on either pin, these functions will be called. In these functions, I set a flag that gets read during the main loop. So the order of events is, the main loop is running, but no flags are set, so it will keep doing nothing forever. Then, one of the motor signals changes from low to high, and the corresponding flag is set. On the next loop, the appropriate signal will be generated. Notice that if the right flag is set, the pattern gets generated backwards. This is because in the original system, the motor runs in both directions, so the pattern will need to be mirrored when the motor moves backwards. You can see in my test run that channel 2 going high causes the pattern to be generated this direction, and channel 1 going high generates the pattern in the opposite direction. Next step, test it on the machine. On the left, I've pulled the motor signals off of the control board and put them into the tops of the voltage dividers. And over here, the white line goes to data and the blue line goes to ground. I did not connect the power because my Arduino is being powered over USB from my laptop instead. I pulled out 62 needles for testing. The middle 60 will hold my pattern and the outer 2 will always be held forward by the machine. I also set the machine for the maximum pattern size of 60 by 150. Though technically the number of rows doesn't really matter because the Arduino will always send the same row. For some reason it missed the first couple rows. I'll have to debug that later. But on the third pass, we start seeing the pattern come through. This is the same asymmetrical pattern that I showed on the logic analyzer. I wanted to see that moving in both directions generates the same pattern. And say for that extra blank row, it looks like we do have the same pattern in both directions. Now I'm going to try to run a pattern across the entire 60 needles to make sure that everything is being pulled forward properly. I'm going to use this pattern of all 5s. 5 is 0, 1, 0, 1 in binary, so this will pull forward every other needle. That looks great. Everything seems to be working as planned. Now let's try to do something a little bit more interesting. I've modified the code so instead of a single line of pattern, I'm able to input a whole array of patterns. So this one is 56 lines long, and if you squint hard enough, you can kind of see the smiley face that will be created by this pattern array. I've had to add a pattern index variable so that we can keep track of where we are in the pattern as we go through the different loops. And you can see every time a pattern line is generated, we have to update the pattern index. Once the pattern index reaches 0, we wrap around to the beginning of the pattern again. Yeah, I'm pretty excited about how this turned out. There's a few pattern inconsistencies, but overall, looking really great. I'm excited to try more patterns with this. Thank you for watching to the end of the video. I really hope you enjoyed following along with my engineering process. This pattern signal replacement is a huge improvement to what I had previously, but there's still a lot of work to be done. I think the next steps for me are going to be either writing some more software to upload a pattern over USB, or work on continuing reverse engineering this main control board so that I can make the pattern wider than the 60 bits that it is right now. I think that I'll be able to make these videos at about monthly cadence, so if you enjoyed this video and want to see more project updates, please subscribe, and I'll see you next time.